All right, let's get started on this kind of chilly day here. I know we have a couple more people on Zoom than normal because of the weather. So we'll get started today. Um, this unit, we're starting unit 2, and we're actually going to, I like this. This is where we actually start talking about some of this theory stuff. We look at Backus-Naur form and how we would define languages here and set that up. And I think it's a fun week. So normal Tuesday for this class. So we'll go over the learning resources. I'll talk and introduce this material for like half an hour or so, and then we'll let you work through some of the prompts and read through some of that stuff and prepare the QQTP that you need for Thursday, and then we'll use that to continue our discussion on Thursday. So let's jump into the learning resources here and get started there. Um, so there's a free textbook out there for a public domain one for programming languages, and it has some theory stuff. So that's what we're going to look at today is this Ken Slanger. He's at the University of Iowa and has this textbook out there. And we'll be using that when it fits here. So and this is a good chapter for that. So I'm just going to open this up and talk and use that to talk from introduce these topics. I'm actually going to scroll down to the example and walk through the example first as a way of looking at this stuff. So we're going to work with defining these languages and or a what we would call grammar. So grammar is a definition for how you make statements or sentences in a language here. And in this example, we're going to do a kind of an English-like one, but we'll use this to generate Java, or other languages, Python statements or Python programs and stuff like that here. So this is going to be made up of what we call production rules, which are kind of like assignment statements or substitution statements. We'll have a symbol on the left side. And again, these symbols will often be in greater than less than brackets. So like sentence here. Then we'll have a special production rule or kind of equivalence or assignment statement saying that if you have a sentence, you can substitute for that. And so again, that'll generally be used colon equals here for this. And then we'll have other things. So like here we can say it has a noun phrase and a verb phrase and a period. So to make up a sentence here, we would start with a noun phrase and a verb phrase and a period for this. And we can actually start this up. Let me just open Notepad as examples here. So the idea is that if you started with a sentence here as your starting point, what could you replace that with? So if you start with a sentence and you have these rules, well, we're on a look for places where where sentence is on the left-hand side, and the only one is this. So the only option we have when we have a sentence is replace it with this. There's only, in this example, only one kind of sentence for this. And this is to replace it with a noun phrase and a verb phrase. See if I can kick this font up a little bit. Okay, so if we have a sentence, we can replace that with a noun phrase and a verb phrase, and then a period for that. So that's what we have now. We want to build from there. So like, what is a noun phrase? So we're going to look at all of our rules, see if any of them have a noun phrase on the left-hand side. And there's only one here, noun phrase as assignment. And there's this. Now this is a little more complicated. And in this place, we have an or symbol here. So this is a new symbol. Is a vertical line is for or. So this means noun phrase can be either this, or I mean, determiner and noun, or determiner, noun, and prepositional phrase here. So you can choose. So we can pick between this. I don't love this written with the or. When I write these, I would tend to write these as two separate rules. Noun phrase is this and noun phrase is that, and you can choose between them. But some authors will write these with the or here. So I'm going to do this. I'm going to say, oh, we can replace the noun phrase with this. So again, if this is our sentence so far, we can now substitute for the noun phrase. We can substitute determiner and noun. So where noun phrase was, we can replace that with determiner and noun. And then verb phrase and period is still there. So all we did is do this substitution. And so this is how grammars are built. We have these, what we call production rules or substitution rules. We can substitute. So again, we can choose to substitute any of these things here. So maybe we want to do determiner. What is a determiner here? So let's see. We have a rule that has a determiner here, and we do. Here's our determiner rule. It can be, we can put in a or the. So we can choose either of those. I'm going to choose the and put that in here. Now, I notice so far every object or symbol we've had has been in braces or in this brackets greater than less than here. When we have a symbol that's not here, that's our kind of terminal symbol or a final symbol in like our language here. And in this case, they're also bold, but they don't necessarily have to be in bold. So it just, because it doesn't have any, it's a terminal thing. It doesn't have the greater than less than around it. We can't substitute that anymore here. All right. So now what else? We have a noun. So again, we can put a noun in here. And again, for noun, we have a choice: boy, girl, cat, telescope, song, feather. So again, we can choose any of those here. So let's just pick cat, I guess. So we're going to substitute for noun. We're going to put in cat. Oops. Yes. Cat as our object. Now we're still, and we keep doing this until we have no more of these, what we call non-terminal objects. So again, we still have this verb phrase. So we have to substitute that. So here's our verb phrase. We can do either one of these. We can do just a verb. We can do a verb and a noun phrase, or we can verb, noun phrase, prepositional phrase here. So if we wanted, we could just say our sentence could be the cat sang. The cat sang, and that would be enough there. So that's allowed. We're going to use this one. So we can do a substitution. Verb phrase can be a verb and a noun phrase. So again, here's our verb phrase can be, oops. What I'm supposed to be doing each time to get this right is I'm supposed to be repeating this so that you see how it's built up. I'm not doing that very well here. So I'm going to go back. So we had noun phrase, verb phrase here. And then for noun phrase, we replaced it with this. A determiner, noun phrase, verb. Okay, now once we had that, we replaced the determiner with the. And then once we had that, we replaced the noun with cat. Okay, now this is what we have. I have to just remember to make copies of this. Each cat, verb phrase. And again, for our verb phrase, we're going to grab this determiner, verb, and noun phrase. So the verb phrase is going to be replaced with a verb and a noun phrase. And again, now we can do any substitution to a verb. So verb, those are what we call terminal things. So saw, touch, surprise, sang here. So let's do saw for our verb. So we have the cat saw, and then we need a noun phrase here. So we know our noun phrase is a determiner and a noun here. So we're going to substitute that in here. And our determiners, we can say the or a. So let's just choose one of those. We'll choose the. And we're getting there. We're almost all terminal values. We just need a noun now. So we're going to say feather as our noun. So we end up with the sentence, the cat saw the feather from this language for this. So that's where we take this stuff and we start with an object and we keep going until we're just all what we call terminal items for this. And again, the text actually walks you through another one of these here. So sentence becomes noun phrase, verb phrase. Then we take our noun phrase and make it a determiner and a noun, and we still have our verb phrase. And again, we go through this, and eventually they end up with the girl touched the cat with a feather as their sentence here. So it just shows how these production rules go. Does this make sense? So this just shows how we can do this stuff. It used to be more common that when we learn computer languages, we actually taught this sort of stuff here. In fact, I wanted to do it on the camera, but I couldn't get it to work this morning. I don't think our document camera is working very well. This is one of my first programming language books called Pascal. I don't know if you've probably never even heard of Pascal. It's an old language here. Let's see, when was this printed? So 1978 is the newest print. 75 and 78 when this was up. And this is how I learned this language here. And much of it has, it has right in it the BNF of the language with details on how it works. Let's see if I can get that. Oops, I'm going to switch. Yeah, switch. So it is going to do, it has the full BNF of this language with all the rules here. And it just takes, the whole language is just 3 or 4 pages of descriptions of this language here. And again, that's what was often taught with this. And similarly, here's my copy of C by Carnegie and Ritchie. Again, really old. And again, in that language is the actual, there's a chapter called The Grammar of the Language. And it is just all, the whole grammar, the whole language is given in this grammar. So it used to be, this is how we'd actually document languages. We've since learned that maybe that's not the best way to teach a new language there, but and I don't know if we really see those much, but again, behind all these languages is an underlying grammar here. So let's go up at the top here and back up and talk about this stuff. So just, and again, this is more like from a math point of view here, where we do formal definitions. So here's a formal definition for our grammar. It's going to contain 4 parts here. So the first part, sigma, is just a set of terminal symbols or alphabet of the language. So in our example here, the terminal symbols are these bold-faced words: cat, boy, girl, telescope, song, feather, the, saw, touched, surprise, sang, by, and with. So that set would make up our terminal set. So that's one thing you need, is a set of terminals. That's basically all the allowed words in your language here. The other thing is you have non-terminal symbols or syntactic categories. So you have another set, and they're calling that N. We're not going to worry about which letters they use to represent this stuff. So non-terminal symbols here. And again, those are all of our examples, and we will put them in a greater than, less than tag here. So like sentence, noun, phrase, verb. And again, in our grammar, every example, everything on the left side of a production rule is a non-terminal example of that. So these are all of our non-terminals. So we have 1, 2, 3, 4, 5, 6, 7, 8 non-terminals here. Okay, so we have those. So we have non-terminals, and we have our production rules. And again, that's what we've been seeing. They describe how each non-terminal is defined by us in terms of terminal and other non-terminals. So substitutions you can make with that. So those are our production rules. And then finally, we need one or more what we call the start symbols. What do we start with? And often this is kind of implied here. So like here, this grammar, we really don't note which one. Often it's the top set, rule will be the starting symbol. So sentence, and sometimes it'll be marked in some places with a special font or a special symbol there, a star next to it or something like that. But in this case, it is just implied that the first rule, sentence, is our starting symbol. So again, when I started this off with sentence, and then I built from there. And again, same here, they started off with sentence and built from there for this. So that's our grammar and stuff. Now, why are we doing this? One of the reasons of making this formal is that we can do a lot of mathematical proofs and stuff with this sort of system here. If we define this stuff formally, from a math point of view, we can do much more way of proofs and rules and stuff like that here. I'm going to back up even just a little bit more. The start of this chapter talks about specifying syntax, and it lays it out in 3 different things: syntax, semantics, and pragmatics. So syntax is what we're going through, is how can you combine symbols to create what are called well-formed sentences, legal sentences in our language. Semantics is the meaning of this. So let's look at semantics here, just so we understand. We'll look at this example again. So in this example, I can choose different things. So let's just back up a little bit here and see what I can choose. So here, except for like a verb, I could choose any verb. I choose saw, but I could choose any saw, touched, surprised, sang. So I could choose sang as my verb here. And always use that. And again, noun, phrases. So now I could easily create a legal sentence that said the cat sang the feather. Now, semantically, as far as meaning goes, that doesn't really, I mean, what does that mean? Say the cat sang the feather. Okay, so syntactically, that is correct. Semantically, that doesn't make sense to me. I'm trying. Now, part of me just wants to take that phrase and feed it into one of the AIs that generate images and see what kind of image we get if we say the cat sang the feather. I mean, I'm just kind of trying to visualize this, but so it doesn't seem to make sense. So again, that is semantics here. And again, we'll talk about that later. Right now, we're just dealing with syntax. How do we generate legal or well-formed sentences or programs here? Now, we'll also talk about pragmatics. One of our books is called Programming Language Pragmatics here. And that deals more even with higher level stuff. What are we implying with this? What is being done, kind of, with a program? It can maybe be syntactically and semantically correct, but then, is it doing what we want? Some of this higher order function. This comes from actual natural language processing, but sometimes we talk about it in scope in computer languages. So, okay. Let's just talk a little bit about the types of grammars here. So again, with these rules, we can generate lots of stuff. So often, well, sometimes I'll try to group the types of languages we can generate or grammars we can generate here. So we start with type 0, which are called unrestricted grammars. And what that says is that you can have on the left and the right side basically anything. On our rules, generally anything, you can often have anything on the right side, but this says you can also have anything on the left side. You don't have to have a single symbol. So you can say, you can start with a terminal, a non-terminal, another terminal is assigned to a terminal, non-terminal, and another terminal, something like that. So you can have multiple things where, again, when we looked at our first rule, we always had just a single non-terminal on the left side here. So if you allow anything on the left side, we call that unrestricted grammar here. If the right side has to have more symbols than the left side, meaning that we can at least get rid of terminals or non-terminals this way. So again, we have in this case, a non-terminal thing and a terminal B, and then we're saying we can replace that. So if with a non-terminal, or non-terminal and two terminals, a B and a period, thank you. So they can talk about that. So then we're getting to what we call context-sensitive grammars here. Now, if we get down to this where the left side is always a single non-terminal, and this is where we'll live in this class. We're in context-free grammars. So we will always be working with rules where the left side is a single non-terminal value here. And those are what we call context-free grammars here. There's also something called regular grammars. There's ways of specifying this stuff in other ways, regular expressions here. And regular expressions can't show everything that a grammar could do for this. And so if there's an area where we talk just about regular expressions, but it's a little less lenient for this. So, but again, we'll be specifying just context-free grammars. In fact, if we look at Unit 3 here, Unit 3 is, I think I just titled it context-free grammars here. So Unit 3 will be, oops, I don't have a context here. Well, unit 3 is context-free grammars here in my list for that. So, okay. Let's look at some more examples of this and how we specify. So we looked at this grammar and we looked at these production rules, and this is what will generally, this is a nice mathematical kind of way or a symbolic way of doing this, which is nice. We'll also at times work on this a parsing tree or derivation tree, which will show us, we'll start with a sentence and then we'll break that into 3 parts, a terminal, period, a phrase, and then again, we'll show that, oh, we took this noun phrase and we created this and this, and it'll show this. And how you kind of read the final things is you start at the left-hand side and just read the terminal. So the girl touched the cat with a feather. Here's the final sentence for this. So a derivation tree is another way of thinking of this. And this will become crucial when we get into parsing and trying to understand statements in a computer point of view for this. We'll talk more about this. Another way of showing this is like a dependency graph here, what depends on another one. I learned how to do something called syntax diagrams, which are kind of flow diagrams for this. Let me see if I can bring up. I expected at this point just to be able to show my book, but again, the document camera just doesn't seem to be focusing here. So let's look at this one. So like this tries to show like how you could create a simple expression with greater than a Boolean like expression. You could create a simple expression. So you have these arrows and then you follow through and you can see the branches. You could take a simple expression and you could choose one of these like a greater than or less than symbol or an equal sign. And then you can have another, then you'd have to have another simple expression and then you'll be done. So it's just these kind of flow diagrams to show how you can create these things. And sometimes there's loops in here or choices. So like here, you can either not, like here's an expression, a simple expression. You can either have just a term or a minus in a term and a plus in a term. And then you can go in here and you can have either a plus or a minus and another term here. And then you can repeat this and have another plus or minus for this. So you could create some, and a term could be like X or Y. So you could create, or like a number, I guess. So you could have a simple expression like 47 plus 18. You could say 47 and then plus, and another term like 18 and finish up there. So just a diagram of that. So again, there are different ways. Now, this doesn't help that much from a theoretical point of view to use this to prove things. This sort of visual way might help you visual or me visualize things, but from a mathematical point of view, it's not all that helpful here. So we will tend to kind of stick with our BNF format for these here. Okay, I'm going to stop here in the textbook again where we get into context-sensitive grammars. We'll talk more about those next week. This week, we're really just trying to figure out how this BNF format works for us. So we're going to go into the prompts and have you work with those. So, trying to think of these, yeah. We have these supplemental textbooks, and you could look at those. So Scott's programming language pragmatics. Now you know what pragmatics are a little bit more. His chapter 2 is also is on programming language syntax. It's interesting. There's not a great common like language or symbols in a lot of these things. So although he uses BNF form, he really doesn't talk about it and what it is exactly. He just uses production rules here. And similar with Sebastian, chapter 3 is on describing syntax and semantics here. And again, I'm not a big fan of how that text goes over this. Again, similar rule or format, but a little more theoretical than what I want. So I've chosen, that's why we're using this text. I really like this BNF format. So given that, let's go into the prompts here. So you can open this up, click on this link, open up the prompts. Again, you'll want to make your own copy of this. And again, I'm going to let you go through here, pick your favorite AI and start working these prompts through the AI system here. So again, I'll just go to chat, not calendar, let's try chat. So if I'm here, I would start with this first prompt to kind of lay the foundation here on what we're expecting. And again, here's you can just take this second prompt and describe this. What we're looking, we talked a little bit about syntax semantics. You can go through that here. Okay, so just go through this prompt stuff. I like to then just paste the responses in here so you can see what they are. Start working for that. Okay. I'll pop in a little bit. We'll talk about this. One thing to watch is, again, some of these AI are not great at mathematical equations. So sometimes these production rules get into that. So what I'd really like to see is, I'm pretty sure we'll get some examples here of like BNF that's not accurate. So watch for that, and we'll want to point that out there. They do okay. Well, yeah. So see how that goes. I'm going to pause the recording, let you work on this each on your own for a little bit. Okay, I'm going to break in again a little bit to point, highlight a couple of sections. So at the very first thing we talk about is recognizers versus, let's see, yeah, versus generators. Here is one of our first questions after we get through the semantics and stuff. What is a language recognizer and a language generator? I just want to go over that real quick. So I have it generate a simple BNF later on here. Oh, let's just go here. Where we're generating numbers. A number is either a digit or a digit and a number. And then the digits are 0 through 9 here. So we can use this to generate a legal number here. So again, we can start with our, let's say, number, and we can say our number is going to be a digit and a number here. And then we can take that a digit and a number, and we can replace that here. So we can say a number is a digit and a number. And again, we can take a number like 6 and put that in here. So now instead of digit and number, we now have like, instead of a digit, we can just pick a digit 6 and then a number. And then again, a number can be just a digit here. So now we're just going to take this and replace this with just a digit for this. And then a digit can be any digit, so we can replace that with 2. So our legal value, number is 62. So that is using a grammar to generate legal or well-formed sentences or statements or stuff like that. Another question we could ask is recognizer, right? Can we is this a legal number here? And how do we use that? And again, we can do the same thing. We can start with this rule here, but it gets a little more complicated. So we'll talk more about this later. We have to try out all the different possibilities. Well, like number is this, it can be a digit or a digit and number here. And here it's obvious to me, well, if it's a single digit, I know that that's just a single digit. This isn't going to work. So I can rule that out. But generally, we'd have to try out all the possible trees of substitution and see if any of them generate this, or how do we generate this. But the idea is that we would try to walk through this and say, okay, we're going to say that a number can be a digit and a number here. Again, because I'm saying 4 digits. And again, that can be the number can be another digit and a number. And then that can be, the number can be replaced with a digit and a number. And that can be replaced with another digit and a number. And so we can certainly create a 4-digit number that way. And then we can start doing our next substitutions here. And we can stick in this digit. We can replace with a 7. This digit we can replace with an 8. And we don't have to do left to right. We can just say this digit here can be replaced with a 6 here. But now we're left with this, and there's no way to generate an A because A is not a legal digit. So we get down to this point and say, no, at least on this, I can't find a way to recognize this as a legal number. And again, when we get to compiling stuff and parsers, we'll create a more formal way of doing that. Okay, so that's one thing I just want to point out. The other thing is pay attention a little bit to BNF and extended BNF, eBNF, and see the difference. So like here, you'll see we're doing number is assigned. And again, we have this colon equals digit or digit number. So we can see that repetition. But in eBNF, we just write it this way. A number, and then we use equals a digit or, and then this parentheses means 0 or more of these things. So 0 or more other digits as a way of expressing this. So just so sometimes, and again, some of the text, some of the versions will jump between BNF and eBNF. So just be aware of some of the symbols that are used in both. Okay, I'll let you go again. And again, I'm looking for AI that generates a bad grammar. Particularly watch for a grammar where, again, like in BNF, every non-terminal that's listed somewhere on the right there has to be at least one rule that has that non-terminal converted to something else so we can get rid of it. We eventually have to get down to all terminals. So see if you can find a mistake in AI where it generates a thing. This looks good. Expression is term or expression and term. Terms are defined by factors or terms. Factors are defined by expressions and numbers. And expressions are defined up here, or numbers. Numbers are defined here. Numbers are digits here. So everything seems to be pretty well defined in that. So I'm looking for an example where here, like I thought this might be a problem because I didn't see expressions, but that's actually what we started with above here. Okay, so let me know if you find one, or I'll ask around in a couple more minutes. Okay. Any questions while we keep going? All right, let's talk a little bit. Did anyone find examples of like grammars that they thought there was a mistake in the grammar? Can you explain one? So, anyone online find anything? It has to end without the term. Well, somewhere where it just doesn't make sense to apply all the terms, like, it defines a term, it uses a term and doesn't have a rule that uses that term, or it tells how to do that term or something like that is often where it gets wrong. So, well, we'll see in the QQTPs if we see some examples of this. I find that depending on which AI system I use, some of them make mistakes more often. So like right now I'm using ChatGPT 4.0 mini, which is relatively fast, but it's 4.0, so it's pretty good for reasoning. In fact, whenever I generate stuff, it'll tell me it thought about this for like 20 seconds or 5 seconds or something. So just, it does more than just a standard language model where it just generates text there. So it seems to be doing okay. Let's look, at some point you looked at expressions in Java here. You asked it to show BNF for an expression in Java. So what is an expression in Java here? So generally, like an expression is just like what might be on one side or another of an equal or greater than sign or something like that, or an assignment statement. So you might say X equals, and then you'd have an expression there. So here's an example of an expression. I think this is a legal expression in Java. Parentheses hours minus 40 parentheses times overtime here. So we have two identifiers, hours and overtime. We have a number. We have two operations, a minus and a multiplication, and we have some parentheses here. We should be able to generate that with our grammar here. So if I look at this, this is the grammar that it generated here. So here's our expression. For this, and so then I can work with this, and it can be I can do this minus here. So I'm going to do this one since I have it. Now this one starts with an expression, and it so if I start with an expression, it has then it works in terms next. So I'm going to do this expression here. Oops. To start working on my, to get my subtraction in there. So now I've got my subtraction in here for this. So I'm actually going to put this down here. And then I can, like, my term for this, if I look through my list, where a term can be either a term, and I can do some multiplication there. So again, that's for the term. Let's try to do the multiplication stuff in here. So the term can be replaced with a term multiplication of factor here. So I'm going to try to do that here. And again, one thing I suggest sometimes is just to play with these rules, because it's okay to read these, but then when you start actually trying them out, you'll start kind of getting to know them a little better. So this term I can replace with a term multiplication and a factor. So I'm getting a little, I've got my minus and I've got my multiplication in here and a factor for that. And then like factor, I can put parentheses around that if I want, or I can just have an operator. So I'm just going to replace that with an operator here. So my factor can just be an operand. You can substitute that in there. And my operand can just be an expression or an identifier here. And once I have an identifier, I can use that. There's this rule. Identifier is a Java letter, and then one or more or zero or more other letters or digits here. So I need to have a letter and letter digits here. Now, it's interesting here, they define lots of literals, but they don't. This is what I would consider an error. They don't tell me what a Java letter actually is in this grammar or a Java letter or digit. So I think I would say that's a mistake in this one. They should have those defined. So a Java letter should be anything between a single letter between A and Z lowercase, or capital A, capital Z lowercase. And a letter 0 should include that and a digit or something like that. So they don't do that. So there's an error in this example now that I start playing with it. But in my mind, I'm saying, well, I can just put what they're really saying is you could write a phrase like overtime here for that. And then now, so that's this here. Now I have to build this up. So I've got my expression. So like I want to get hours in here. So I can work on that. Now, one problem I have is that how do I get the parentheses in here? Right now, it looks I should be able to convert my term down to 40 and my expression to hours. So I think I should be able to take this and with the production rules, get it to hours minus 40 times overtime there. I guess I could take the quotes around the expressions here, but I could get down to this thing. But I need parentheses here. And how do I get those parentheses in here for this? So the only place that I can see parentheses in this is with this factor here. I could build a factor. But I don't see a good way of getting that factor in here. I guess for my term, I could put parentheses in there here. So for term, I could convert the term into a factor and the factor into parentheses. So let's try that route. So again, I'm going to go, I've got this. And then for a term, I can just make that into a factor. Okay, so I got closer. Now, factor can be this. And now I can get my parentheses in here. Parentheses and expression. And so now I can start doing my expression again for this stuff. but now all my format's not looking quite right. And so that's one of the things that sometimes a challenge is if you're trying to build something here, how do you find the right path to do it? It's easier to generate a legal expression than to test out if this is going to work for this. Now the question comes up is there an error in this grammar? Can I generate this grammar? Can that be used to generate this expression here? And so that, again, that's a good challenge. Can you, what would you have to do? Expression to term, term to factor right away, factor to parentheses with an expression there. But that would let me do this, but not this multiplication here. So can I go expression to term, term to term multiplied by factor here to get the multiplication in here first. And then factor from term to create that, so how do I do this? And so you can actually set this all up to do it correctly, but you have to be careful on the order you want to set these rules up. So, let's look at if-then stuff. So did you ask, one of the last questions was, go down to your final question if you got there, comparing a Java with Python if statements. How did those look to you here? I find sometimes so these explanations aren't the best with this. So like here's Java syntax. If some condition, parenthesis, parenthesis, and else if another condition, parentheses, else. Now, again, it should be noted that these else's are optional for this. And so that's not really clear in this description here. But when the syntax, it should be pretty good. So how does it define the if statement here? And did yours give the same definition? If statement is the word if, a parenthesis, an expression, another parenthesis, and then a statement. And then, again, this is using eBNF here. It says BNF, but this is really eBNF because, again, and then it's a brace, meaning this is optional, optional else, and in another statement for this. So this looks pretty good here. And then a statement can be a block, which means we can put in the parentheses around it. I find this kind of confusing because they're using eBNF, which uses the squiggly parentheses to say you can have one or more statements. And we also have parentheses in there. So they do use quotes to denote some of this stuff here. And so it gets kind of confusing with these languages when the symbols we use to denote BNF or eBNF are also part of the language for this. So how did your program define the Java stuff? Did it look similar to this? Did anyone have, to me, this shouldn't be an expression. This has to be a Boolean expression. So did anyone find that it generated a Boolean expression for that? Because to me, that's an error because you can't say if X plus 10, where it's not, it has to be a Boolean. It has to have a greater than or equal to some comparison in it. You can't just say if overtime plus 5, it has to be a Boolean expression there. So I was surprised. If I were to write this, I would put a Boolean expression here and have limits on that. So. Yeah. You had Boolean. What model? Who were you? What system were you using, or what AI? Okay, Claude. Okay, that's good. Yeah, I'm interested to see. And while you're doing this, you should watch how this works here. Again, one thing we want to watch is like in Java, these braces are optional, right? If you have a single statement there, that would work okay. So that's what they're trying to show here. Statement is either a block, which has the statements inside parentheses, or you can just have, and I find this a little confusing, they have an expression statement and an if-then statement here. They don't have, so you could have another if here, or again, an expression statement. I don't know what they don't really define what an expression statement is. So this was kind of an error to me. I'm not sure what an expression statement is, but in a full version of Java, we would have like a generic statement here that could be put in here. And we'd have a list. Every statement could be replaced with an if or a assignment or something like that. How about Python? Now remember with Python, we say if some condition and then a colon. And then rather than braces, we have forced indenting, either with tabs or spaces. And they always have to have the same. And then there's an else if, an elif, and then an else. And again, the elif and the else are optional here. This is how mine did it. We have an if statement is the word if, and then an expression. And again, I think this should be a Boolean expression and a colon, and then the suite here, and then elif expression colon and what they're calling a suite, and elif colon and a suite. So this is kind of like a block here. And what they're saying is that the suite can be a simple statement. So in Java, in Python, you don't have to put a return. You could just put colon in the statement here. Or you could put a new line, an indent, and then a statement here. Plus a dedent here. I don't love this explanation. Did anyone else get, what did yours say as far as the, Python, how do you generate an if-then statement? So you should look at yours and see if you can make sense of yours. If you think yours makes more sense than this for this. And how they set that up. Okay, let's wrap up. So again, for Thursday, make sure to the discussion area you post your QQTP here, a question, quotation, talking point. And again, at the bottom of this, you can just put those in. So quote something from your AI or something like that, a question you're having and a talking point. And we'll go through those on Thursday at the start of class. All right. Any questions, online people? Any questions, comments before we wrap up? In class? All right, stay warm out there, everyone.